we go. Okay, so in this most wonderful edition of ENGR 425-R, I said it's more or less a review day today. We'll have an example of Prandtl-Meyer expansion waves first, but then Ian, since it looks like you're the person here, it's for the rest of class, up to whatever questions that you got. Okay.
Okay.
Cool. So Prandtl-Meyer expansion waves. So what can you tell me about Prandtl-Meyer expansion waves? What are the assumptions that go into them?
So we're assuming they're an adiabatic process.
Okay.
And that they are an isotropic process. And, yeah, isentropic.
Okay. So if it's isentropic, what does that mean besides just being adiabatic?
That the total pressure is the same across it?
That's true. In an isentropic adiabatic process, not only will the total temperature stay the same, but the total pressure will as well. That is very, very true. What does it mean about our assumptions about what forces are acting on it?
We're assuming that there are no viscous forces and no losses.
Yeah, which call that. We don't have any non-conservative forces. Friction's a non-conservative force, or viscosity. Viscosity would cause non-conservative effects. So yeah, excellent. So it's viscid, adiabatic, and the process is reversible, so it's isentropic. Great. The entire thing's isentropic this time because there aren't any shock waves here. So what's the difference between a shock wave and a Mach wave? Because we know that an expansion fan, which would be like that thing, we know that that's not a shock wave, but we were describing it using Mach waves, which would be like these constant pressure lines that are marked out here.
Mm-hmm.
So, like, what are Mach waves? What are those?
That's a line where there's constant properties of the speed of sound.
On that line, it's probably true. But like, put it this way, what's kind of how do I want to say this? Why do we care about it? Like what is it? What defines a Mach wave?
Like it deals with the geometry of the way it's moving faster than the speed of sound. I know that.
Okay, cool. Yeah. So the line, you're right. Along that line, you have kind of constant properties, but that line also precipitates. It's a it's a way of demarcating a disturbance. So last time we talked about flow comes up to this. So you have flow, it comes up to this corner here going woo, and it's flowing that way. Then after the corner, it's flowing that way because it has to follow whatever the local geometry is, right?
Mm-hmm.
So around that corner, it's turning somehow, going from one direction to another. And when it turns, we see this expansion fan pop out. This expansion fan, as you said, is made up of Mach waves. These are these lines of constant pressure, which you said are quite rarely are lines of constant property. But what's a little bit more descriptive about Mach waves is that it's not just a line where you have some property that's consistent. More specifically, and a better description of it would be that is something that we can intuit by what changes through the Mach wave. So as I go through each Mach wave, as our derivation showed last class, our flow velocity changes a bit, not just speed, but also direction.
Mm-hmm.
So if I zoomed in really far, that's about as far as it lets me zoom in. Let's pick a point up top here. So you have flow moving this way. As we go through the Mach wave, my direction changes a little bit every time that I go through another Mach wave. It's not that exaggerated here because I'm only changing direction a little bit, but I'm exaggerating to make a point. Each time I go through a Mach wave, my direction changes a little bit. So in order for my direction to change, that means that there has to be a pressure disturbance, right? If there's not a pressure disturbance, then velocity doesn't change. We know that from subsonic aerodynamics too. In order to affect a velocity change, you need a pressure change. So there's some relationship intuitively between these Mach waves and pressure. That's thing one. What we looked at last time specifically was, okay, if we have something that creates a pressure disturbance, like a object moving faster than the speed of sound, or an object moving through air, or here we have a change in geometry. It's kind of the same thing. We're forcing the air to do something different. Whenever you make the air do something different, it means that there has to be a pressure for variation in order to make the air move differently around the disturbance. The disturbance in this case just being a change in the slope of this body here. So going from there to there. You following me, Ian? Does that make sense?
Yep.
Cool. All right. So, okay, so a Mach wave is related to a pressure disturbance. And you might imagine the larger the larger the pressure disturbance that's required to change the flow velocity, you might that might end up being a shock wave on one hand if it's like a compression corner, which would be like this. So the flow has to turn into itself. Nature creates a shock wave in order to handle that. Or if you're expanding, you end up with something much weaker, which would be these Mach waves. But you don't end up with just one of them, because the flow, because there's no, even though it's a sharp corner, the flow is not just turning on a dime. It has to smoothly change from one point to another. Even through a shock wave, there's some thickness of the shock wave, right?
Mm-hmm.
So here it's not just one Mach wave, it's a whole family of Mach waves. It's an expansion fan containing many Mach waves. So where is it going with this? So when I go through one Mach wave, it's only some small pressure disturbance that only turns me so much. Then I go through another one. It's generated by another pressure. It's representative of another pressure front that turns my flow a little bit more. Then I have another pressure front, turns my velocity a little bit more, and so on and so forth. In other words, these Mach waves are pressure fronts. It's kind of how you can think of them. They're indicative of a pressure variation that's going to change the velocity of the flow. Okay?
Mm-hmm.
Cool. So now that we have those, question is, can we solve stuff? All right. So let me dump all that. So let's say that we got some flow coming in here. Woo. Well, that's a terrible color. Let's go back to electric lime. So we got some flow coming in here. And that flow's moving at, let's see, Mach 1.5. It's not, doesn't look it up there. Okay, so that's moving up Mach 1.5. And let's see, what other information we got here? Actually, let me draw this on a piece of paper, and then it'll be easier for you and for me. All right. So some expansion fan there. This is condition 1. That's condition 2. No, M1 is 1.5. Pressure in that region is 1 atmosphere. Temperature in that region's 288 Kelvin. So essentially standard pressure and temperature. And that flow is expanding around a sharp corner, the angle theta. Say that that's 15 degrees. Question is, what are all these in state? What are all these properties in state 2? And my marker is starting to die. Yeah. All right, so that's what our problem is. So what was our procedure for working this last class? What were we talking about?
Well, we set up some of the things that we did with the shockwave, and then we set up the integrals with the theta.
Okay, right. So he said, okay, we have this expression for which call for the turning angle of the flow. And we have it in terms of Mach number, so we can integrate around that turn, and we can integrate across each expansion wave, each Mach wave, and get how much and sum up all the angular differences in the flow's direction that are caused by those expansion waves. We can add all those up, and eventually that'll get us all those little d thetas, that little change in direction there. If we add all those up, that'll get us the total turning angle. Yeah, and we can do it all with respect to Mach number. So we can define this turn in terms of the Mach number before and after, which is great. We came up with this expression, looks something like this. Theta equals the Prandtl Meyer function evaluated at state 2 minus the Prandtl-Meyer function evaluated in state 1. That was just kind of the end of that kind of road. We said that the Prandtl-Meyer function itself looks something like this. This is if this is familiar.
Mm-hmm.
Okay, cool. So we can evaluate that expression for each Mach number, and we know that it's related to the turning angle, or we have a table in the back of the book. Either way, we can get the value of the Prandtl-Meyer function for a given Mach number. Okay, so, and we know the turning angle. So if I can find the value of the Prandtl-Meyer function before the wave, because I know M1, so I know that I can find that. I know what this is because that's just geometry. So I can solve for this guy. No problem. Try to get the other two. So question is, what's the Prandtl-Meyer function? What is the value of the Prandtl-Meyer function when evaluated for state 1?
Hopefully bigger than or smaller than a state 2.
True. Well, you got numbers though. Give me a number.
I won't use that calculator. I'll use it anyways. I really want to use a calculator.
What?
I'm just talking to myself.
Okay. I'm calling, and I'm just enjoying a reverse Polish notation calculator that I found. Also, do you have your calculator in radians or degrees?
I think it's in radians.
Okay, cool. What you got?
Almost there.
Okay.
$11.9.
That's what I got. Sweet. Now what? Now what are the units?
I think it's unitless. Oh wait, yeah, because it's the square root of Mach number, and that should be a unit, and it's the inverse arctangent of square root of Mach number.
It's true, but when you take the arc tangent, that gets you an angle, right?
Oh, yeah, so it's radians, right?
Um, Interesting. What you call it? Depends on how your calculator's set up. I set mine up in degrees, and I got 11.9, which means that my number's in degrees.
Oh yeah, I'm in degrees. It says deg at the top.
Sweet. Yep. Okay, so that means that it's 11.9 degrees, which is great because the angle of our the angle of the turn is also in degrees. So everything matches. Life is good. So that means that the blah, 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 new of I can't talk today. New evaluated for M2 be what 15 degrees plus 11.9 degrees.
Yes.
26.9 degrees.
Yes.
Great. So now you have two options. You can set up an iterative solution and solve this puppy for what the Mach number is for that value of the Prandtl-Meyer function, or we can grab our books, roll over to Appendix D. Actually, you know what? We can be cooler than this. Wait for it. Wait for it. Wait for it. Here we go. Almost there. Okay, we are running. Hang on. And if you look at my screen, the slot where the slides were, you'll see a book. There's Appendix C, value of the Prandtl-Meyer function and Mach angle. So we're looking for, in this column, for new. We're looking at for 26.9. Keep in mind that the pluses are just times 10 to the whatever's on the right-hand side of the plus. So this would be like 0.1427 times 10 to the second power, or 14.27. So we're looking for 26.9. So this would be the closest one there, 27. Oh, sorry, that's times 10. That's the 10th. We want more than that. Here we are. We're down. Oops. I'm all over the place. We're over here. There we are. Let me back up a second. Come back. Okay, so looking at new, 27.75, 26.38. We're right between them. So look.
0.025.
Say again?
0.2025. Oh, wait. So that's times 10 to the first, so 2.025.
Yeah. Huh. I think it's just 205, Mach 205. Oh, I see what you're saying. You're averaging them. Yeah. Good. Yeah. So that means that our downstream Mach number is about 2.025, which is weird, right?
Uh-huh.
Because our Mach number went up.
Yeah.
And we expanded. That's weird. Usually, like in subsonic flow, the opposite would occur. You'd slow down. Well, let's figure out how much we actually sped up by, because Mach numbers normalized is which call our velocity normalized by the speed of sound. So let's see if we can get the speed of sound and go from there. So if I know my Mach number, how do I get all the rest of my information? How do I get pressure or temperature or whatever?
Can we use our awesome things that we made before for cross shockwaves to figure out?
Not across shockwaves, because I'm not going across shockwaves.
Cross isentropic flow.
Yeah. So we know M1 is 1.5. That M2 is 2.025. And we also know that going from one state to another, say for temperature, if I look at, say, my ambient to total temperature ratio, that's something that we have a isentropic relation for. You know that looks something like that. So I can write that for either one of these. And then I know that the total temperature is staying the same. Is the total pressure staying the same too?
Yes.
Yeah. So I can do ratios like that, which, because those two temperatures are the same, they cancel out, and I'm left with T2 over T1 equals 1 plus gamma minus 1 over 2, 1 squared, 1 plus gamma minus 1 over 2, 2 squared. And I know what T1 is. It's 288 Kelvin. So I can just multiply through by that. That's a 2, I promise. And if I can solve that guy, I am home free. So let's have a look. So got my 288. Let's see, then the numerator is 1 plus 0.2, 1.5 squared times plus 1.2 squared times plus 5 times. So it gets my temperature to be, at least I get 229.4 Kelvin. Are you getting something like that?
Squared divided by 229.4. Yep, that's what I got.
Sweet. All right, so that gives us the temperature. Let's get pressure while we're at it. So It's the same deal, except we raise it to the gamma over gamma minus 1 power. Sorry, it's kind of sloppy there. I ran out of space. That's this whole, everything in brackets, that's all raised to the gamma over gamma minus 1. So I can look at that. Let's see. 1, 2, yes. Yes. You should get something like 0.45 atmospheres.
Yes.
Cool. All right. So we said that we were doing all this so that we could figure out how fast the flow is actually moving in each case. So how do we get that from a Mach number?
So we want to get the speed of sound, right?
Yeah. So how do we get speed of sound in each case?
The square root of gamma RT.
You got it. So square root of gamma RT. So let's see, 287, 1.4. Then first case it's 288 Kelvin. So it's 340.2 meters a second in the first case. For those of you who don't like English units, unlike you, I know you're just trying to stand up for the little used unit. So I get like 303.6 meters per second for the second case and 340 for the first.
Mm-hmm.
Cool. So how fast are we moving in each case?
Did that wrong.
Okay.
303.6 times 1.5. And then no, that's the wrong one. There we go. $340 times 1.5. That's what.
Yeah.
So 510 meters per second in the first one, and then and then 613 in the second one.
Cool. All right. So we actually are moving faster by a pretty significant amount too.
Mm-hmm.
Even though the temperature's dropped, we're still moving faster.
Mm-hmm.
It's not just a trick of the cards, if you will. So why the heck would we go faster when you try to expand the flow?
Well, the pressure is dropping, so it's moving from high pressure to low pressure. So that makes sense that it accelerates across that.
That's true. That's true. But if we did this in subsonic flow, we know that that wouldn't happen.
Mm-hmm.
So why is it doing it?
Because it's supersonic flow and it does weird stuff.
Well, that is a fair answer. why does it do weird stuff? Like, yeah, let's jump back in time. It's in here somewhere. I know it is. Oops, too far. Oh, it's in here somewhere. Yeah, something like this. Okay. So we have flow going through this nozzle, comes in subsonic, around somewhere in this throat region, it goes supersonic. You keep on going. Oops, it actually starts to accelerate and keep on moving faster and faster and faster and faster. Awesome. So we said that's weird. We said this wouldn't, if this is a subsonic nozzle, we'd expect the velocity to go back down as you went into this diffuser section, as you start to expand the flow again. But it's supersonic, so it's not doing that. We did say that velocity changes velocity changes occur because of what?
Pressure differences.
Right. If there's a variation in pressure, there will be a variation in velocity. So in this case, say there's some pressure change here or some pressure down here. That information is going to come upstream or it's going to go downstream at some speed. How fast is the pressure information, the fact that it's a higher pressure on this side or a lower pressure on this side, or how fast is that information going to travel?
Speed of sound.
Right. We're traveling faster than the speed of sound now, right?
Mm-hmm.
So that means that we're outrunning anything from upstream. We don't hear it. We'll never hear it. And anything that's coming from downstream, we're getting a lot closer to it before we see that too. So as a result, when I start expanding and I'm supersonic, I never get the note that I have to slow down. All I see is, hey, there's more space here. I need to take up that more space. So my density ends up going down so that I can take up that space, right? But I have to still satisfy continuity. I still have to have the same mass flow rate here as I do here. But now I'm spread out. I have lower density, so my speed has to go up. And so I am expanding, but I'm accelerating because I'm supersonic and I'm moving too fast to see to see the pressure variations from upstream or downstream. That would cause me to slow down, at least for a time. Eventually, I'm going to hit a shock wave because I'll finally see that pressure in information, and I have to slow down. And nature's way of slowing down supersonic flow is a shock wave. So, does that make sense?
Mm-hmm.
Cool. You can kind of see like the edge of it here. Like you see this. You see this guy?
Yep, like you drew the ellipse out. That would be the shock wave.
Yep, that'd be a shock wave. You just get the edge of it because the flow finally ran into a corner that said, "Hey, there's a thing here. Change your velocity." So there's a shock wave in order to force that change in velocity. All right. So that is that. that's an expansion fan, and that's expansion waves in a nutshell. Our next step is going to be putting them all together with some airfoils and talking about how that gig works. But let's pause for a second. We've got about a half hour left. Do you have any questions that you would like answered or problems you'd like to see worked prior to the test on Tuesday?
No.
Okay. Note that the test will be on normal and oblique shock waves in addition to 3D aerodynamics. So like wings and stuff. All right.
Oh boy.
No questions on that?
Nope.
All right. Well, in that case, let's keep it rolling. You might have noticed that there's a new homework assignment posted. It's due essentially. It is due the last day of class, so you got whatever time you want to work on it. It'll go through everything that we have done in shockwaves, plus a little bit about airfoils, which will at least start today. If not, we'll finish it next week on Thursday. All right, so we've talked about expansion waves. We've talked about oblique shock waves. So I'm going to draw you an airfoil. This is a flat plate airfoil. We used this before when we were looking at subsonic flow, right? It's kind of our first pass at modeling an airfoil. So got our free stream there. We have this airfoil at some angle of attack, so it's making lift. Trick is the free stream is supersonic. So what's going to happen as the flow hits the front of the airfoil? In subsonic flow, what would happen?
It would turn around the airfoil.
Okay, so it would go over the top and then over the bottom, right?
Mm-hmm.
Okay, so let's consider each of those by itself. Let's think of the one at the bottom. So if I'm supersonic and I have to turn like that, what's going to happen?
An oblique shock.
Say again?
An oblique shock wave?
Yeah. So on the bottom, from the tip of the airfoil, that should have gone to the tip, we're going to get an oblique shock. If I have supersonic flow and I turn like this, like I have to do on the top, what does that do? Does it make me a shock wave?
I would think, but I don't know.
Well, is it turning towards itself? Is it is it like a compression corner?
I guess it'd be an expansion wave.
Right, it's turning away from itself. The flow's being made to expand. So getting an expansion fan on the top. And a shock wave on the bottom, which kind of matches with, if you go back to the slides, which call something like this, where something like this wedge guy, where when the flow was coming in and it was forced to turn, when it turned into itself, which would be like this compression corner. That's what a compression corner is. When the flow's forced to turn into itself, it made it made a shock wave. And then when it turned away from itself, be like over this corner, it formed an expansion fan because it's now being torn apart instead of being shoved together. So we're just seeing that. If you go back to the document camera, on a flat plate now, on an airfoil. So if I wanted to figure out, okay, what the lift and drag of this thing are, well, I'd have to find the pressure, say, here and here, right? Above and below the airfoil.
Those look like good spots.
Cool. Good, because there aren't any other spots. So if I'm trying to find that, say P1 is 1 atmosphere. Let's say that Mach number for the free stream is Mach 3. So how do I figure out P2?
We do the relations across a shock wave.
Sweet. Okay, so how
But
do I?
not any shock wave, an oblique shock wave.
Yes, across an oblique shock wave. So I know my upstream Mach number, but so if I'm thinking of relations across the shock wave, all of them needed what?
Theta, beta.
Right. So how do I get theta? What is theta?
So would theta be the angle of attack?
Why?
Just thinking about like parallel included angles there.
Yeah. Oh, like if alpha was 0, the flat plate would be like that. The flow would run right over the plate, and it wouldn't be, and it wouldn't be turning at all. So yeah, the more that I incline that plate, the more the flow actually has to turn. So alpha is identically how much the flow has to turn in this particular case. So our turning angle, or theta, is the same as our angle of attack. So if I have a Mach number, I have a turning angle, what's my wave angle? What's the angle of the shock wave? Alpha equals 5 degrees, by the way. I forgot to write that down.
Upstream is 3. %5 grease. So like 21 degrees, 22 degrees for beta.
That sounds good. That sounds good to me. All right, so we got that. So how do I get the Mach number normal to the shock wave?
Then we can use our
Our trigonometry, because we know that beta is measured from the same place that alpha is. At least if you think of it like a opposite interior angles kind of way.
Uh-huh.
So that means that the normal Mach number, the normal free stream Mach number, would be like M1 sine beta. in this case, like Mach 1.124. And if that's the case, we should be able to figure out which call. Then we can go back to what, our normal shock relations.
Uh-huh.
And what do we get for pressure variation across the normal shock wave? If your upstream Mach number is 1.124. Should be able to find an expression that looks something like this.
So that multiplied by our upstream pressure, which is 1 atmosphere, is so that's 2.76 atmospheres downstream.
3.76. I am inclined to believe you. I'm just double checking. I got 1.3. Yeah.
That's a problem. I had to multiply it instead of divide by the gamma plus 1. Don't know how that.
Yeah, that'd be a little problematic there.
So 1.3 atmospheres.
Sweet. If we multiply all that by P1. Okay, so.
That's P2.
Yep. And then P3 is just an expansion fan. We know that we're going around a 5-degree turn, right? So we can, if we really want to cheat, we can just pop into Appendix C, say the value of the Prandtl-Meyer function for Mach 3 is 49.76 degrees. We know that we're going around a turn of 5 degrees. So that means that nu for state 3 is what?
Wait, how do we get the 40? Oh, that was the 22 plus our.
Say again? Oh, nope. This thing here. You're asking how I got that?
Uh-huh.
Okay. 1 second. Let me pull it up. Okay, you see the book?
Mm-hmm.
Okay, so this is Prandtl-Meyer function at a particular Mach number, right? So the free stream Mach number is 3, right?
Okay.
And I know that the turning angle is the difference between the Prandtl-Meyer function before and after the expansion fan, right?
Mm-hmm.
So I can look at the Prandtl-Meyer function. Here we go. You're at Mach 3. The value of the Prandtl-Meyer function is 49.76.
Uh-huh.
I can run the numbers through the equation, or I can just look it up here, and it honestly doesn't make a difference. It's the exact same thing. One just you can have a little bit more flexibility with.
Okay.
So there's my value of the upstream Prandtl-Meyer function. I know that, see if I'm this cool. I know that, hang on, here we go. I know that the Prandtl-Meyer function, here we are. From downstream minus the Prandtl-Meyer function from upstream is equal to my turning angle. We said that my turning angle is the same thing as my angle of attack here. So alpha equals nu at M2, nu at M3 in this case, minus nu at M infinity. So if I add my 49.76 degrees I just got from looking up the value of the Prandtl-Meyer function at Mach 3, if I add that and my turning angle, which is my angle of attack, which is 5 degrees, that gets me my value of the Prandtl-Meyer function for downstream of the expansion fan.
Mm-hmm.
Make sense?
Yep.
Cool. All right. So if I do that, it means my downstream Prandtl-Meyer function is what? What's the value of it?
54.76.
Okay, so at 54.76, what's my Mach number?
About 3.25. More than that.
Okay, so let's roll down here, 54.76. Yeah, somewhere in there, somewhere in that region there. Great. All right, so now that I have that, how do I get pressure?
We have a Mach number and
Where's Mach number? That is away.
yeah. So then we set the stagnation pressures equal to each other, and we use that formula to figure out what the Mach numbers are.
Yeah. So we know that I'm just looking at stagnation pressure. I'm going like, hang on, make sure I don't flub this relation. Hang on. There we go. I know that if I'm looking at an isentropic flow, the ratio of pressure to stagnation pressure to ambient pressure is this. And we know that stagnation pressure is constant in isentropic flow. So if I say, those are going to cancel out. We got P2 over P1. And that's going to be equal to 1 plus, minus 1 over 2, 1 squared over plus minus 1 over 2, 2 squared, the gamma over gamma minus 1. So if the upstream pressure is 1 atmosphere, and I know that my downstream Mach number is 3.25, my upstream Mach number is 3, what's my downstream pressure?
0.69.
That's what I get. Okay. 3. Okay, so I got my pressure above the airfoil, I got my pressure below the airfoil. So, assuming that I have a chord length of 1 meter, say.
Mm-hmm.
How do I get lift and drag? At least lift per unit span and drag per unit span. Kind of 2D lift and drag.
So are we just saying that the drag is the induced drag?
Well, in this case, it's wave drag because we have a shock wave.
Uh-huh.
Remember, if we didn't have a shock wave, we actually wouldn't have any drag.
Mm-hmm.
Weird twist of fate. Well, we have induced drag. You're right, but specifically, we have all this because we have drag in our present case because we have the shock the shock wave there.
Mm-hmm.
So
We
how do we find drag?
We use the upward force, the horizontal force.
Okay, cool. So how do we get a force?
Multiply that by an area.
Okay, so we got P2 and P1. Atmospheres is not a convenient unit, so we need to pop those over into something useful.
Like PSI.
I don't know if I call that useful, but I guess, but I guess it's okay. So 0.69 times 14.7, since we insist on using those. That's what, 10.15 psi. $19.11 psi.
Mm-hmm.
Okay, this is going to be 3.281 feet or 39.372 inches. And because it's 2D, we're just assuming a unit span and just multiply things by 1. Okay? Because it's 2D, we're effectively not caring about span. So we got those. So if I did like a summation of forces in the vertical direction, that would look like what?
That would be the
Sorry. Go on, please. What would it look like?
geometry. Right.
Yeah, geometry.
So that's alpha there. We want the away component of alpha.
Yep. So think of it this way. If alpha was 0, it'd be like all of P2, right?
Mm-hmm.
And which calls
sine of alpha?
Well, if you did the sine of alpha and alpha was 0.
Cosine, for sure.
Yeah, there you go. And do I need to multiply by anything else here?
Nope. Well,
pressure is
multiply by 39.372 inches.
Yeah, I need to make my pressure into a force. So there's my force per unit span. then times cosine alpha. That's what's pressing up, right?
Mm-hmm.
What about what's pressing down? How do I take care of that?
Same way.
Yep, except I subtract it.
Mm-hmm.
It's about the pressure difference. So 10.15 psi over the same chord, also times cosine alpha. And that's going to equal my lift per unit span. And I can do the same thing for drag, just using sine instead of cosine. And I got lift and drag. We got a number out of that.
So for the lift, I have 351 pounds per inch span.
Cool. And then if I change the cosines to sine to get drag instead, would I have to change anything else there?
Um,
Not really.
no. Nope.
Nah, because it's all pressing backwards, which is the correct direction.
Uh-huh. And then for drag, I've got 30.7
Units.
pounds per inch span.
Cool. And if I wanted to get lift and drag coefficients out of those,
Then we'd use our lovely formulas of drag divided by Q infinity times S.
yep, except for 2D, that area is what?
0. Or
No,
it's the chord length.
there you go. Yep. That's that. Next Thursday we'll look at this with a diamond airfoil, which is kind of your usual or your basic supersonic airfoil, and we'll start wrapping things up. So, any questions on this, Ian?
Nope.
Great. All right. Well, that's all. That's all we got for today. Then. Thanks for stopping by.
Right. And the exam
Oh yes.
that you said?
Yeah. So test is on Tuesday. Test on Tuesday. It'll be during class time, so we'll show up like this. It's open book and open notes. I'll send you the PDF like 5 minutes before a PDF of the test, like 5 minutes before class.
Okay.
I'll be here via this connection if you have any questions that you need to ask on it. And there'll be a Dropbox for it on Canvas, so you just submit a PDF of it when you're done.
Okay.
Cool. All right. See you then.
See ya.